Okay, so this is our lesson on section 11.6, natural logarithms. And this is the last section that we're going to look at in this chapter. So that means next week we'll have our review day and then our test. So look at this graph. What you should recognize right away is that the green graph right here, this is an exponential function, y equals e to the x, right? And this is Euler's number e. And it's just an exponential function, so it's passing through, of course, the point 0, 1, and tending to 0 over here. And then growing by a power of e, which of course is close to 3. And then if we reflect it over this line y equals x, we get the inverse function of y equals e to the x. And that, of course, is a log function. And it's going to be log base e. Okay. So that's what we're talking about when we talk about natural logs. We're talking about this log over here, which is the inverse of y equals e to the x. Okay, so what have we learned about logs so far? So if you have a log like this, and you have a subscripted b, right here, subscripted b, then that makes this log base b. And if you don't have any subscript right here, then of course that means that it's a common log, and that means that it has base 10. So what we're looking at today is natural logs. And a natural logarithm has a base of e. And remember, e is Euler's number, right? And it's a number that's slightly smaller than 3, 2.718, and so on and so forth. And normally you might think that it would be written this way, where the e is subscripted down here. But the conventional way to write the natural log is just to put ln. Okay. And natural log, right? And then we don't need to write the base, because the base will be assumed that you mean e when you say natural log. Okay, so natural logarithms are used anytime we need to solve problems that involve e. So think about the different formulas we had when we worked with e, like PERT, right? Our formula for continuously compounded interest, and then any exponential function, growth function or decay function that uses e as a base, then we would need a natural logarithm. So anytime that we're working back and forth between natural logs and exponential expressions, of course we go right back to using ELBA, right? So we're still going to convert it, the exponent equals log base answer. And the only thing that's really different about using ELBA is that, of course, this base right here is just going to be e, right? Euler's number. So here's two examples. How do you take the natural log of e cubed? So if you get confused by this notation right here, you can rewrite this as log base e, and then this is e cubed. And then remember, the definition of a log is how do we move from the base to the answer? In other words, e to the what power gives me e cubed. And then of course the answer is just 3. So here's another example that doesn't have any e's in it, right? This is just log base 4 of 381. But if I wanted to write this using a natural log, I would just use the change of base formula. So I'm going to put the log of the base in the basement and the log of the answer in the attic. And that's going to make this the natural log of 4. And that's going to make this the natural log of 381. And then this becomes 4.287. So the natural log is just log base e, and we said that we could use any base we wanted when we did the change of base formula. So you're certainly capable of using natural log if you wanted to find the value of any log of any base. Okay, so our goal today is to solve equations with natural logs. And before we do that, we need to talk about one more thing, and that's the properties of natural logs. So the properties of natural logs are absolutely identical to the properties of all logs, no matter what the base is. They just look a little different because instead of writing log base b, right, we write ln, right? Because of course our base in this case is e, Euler's number. So recognize that you can use these properties just like you could with any other log whenever you're working with the natural log. Okay, so I want you to pause the video here and take about 5 or 10 minutes. I want you to pick at least 3 problems in section A, and then I want everybody to do problem B. So go ahead and pause the video now, and then resume the video after you've worked on these problems and checked your answers. So we're going to look at solving equations with natural logs. And we're going to look at a couple of different types of problems. So you don't always have to use the same method. In this case, we're going to look at a couple of different methods. So starting with equations that involve the natural log themselves. In other words, you actually see the symbol ln. The first thing we always want to do is we want to isolate this ln, right? We want to isolate the natural log. So in this expression, we've got 7.5 times the natural log of x. We need to get rid of that 7.5 by dividing both sides of the equation by 7.5. So this becomes 3.75 divided by 0.75, and then over here we divide by 7.5. So this becomes 0.5 equals the natural log of x. So the next thing we want to do is we want to rewrite this log using ELBA. So what is ELBA? Exponent equals log, here are the bases e, and x is the answer. So to rewrite this, we would get e to the 0.5 equals x. Of course, from here you can just calculate this because you can plug e to the 1/2 in your calculator and you get x equals 1.65. So that's what it looks like when we have equations that involve the natural log themselves. But the natural log can be used in other situations. In other words, any kind of exponential function can be solved using a natural log, even if you don't see ln in the problem. So let's take a look at, let's take a look at this problem. Okay, so now we're looking at part C, solving equations using natural logs. So here's my problem, 4 to the 3x power equals 6 to the x minus 1. And you notice that there's nothing that says you have to use a natural log, but we can use one nevertheless. So the first thing we can do is we can take the natural log of both sides. So this would become the natural log of 4 to the 3x equals the natural log of 6 to the x minus 1. Now, since we have a power, here and here, remember that when you're taking the log of something and it has an exponent raised to it, you can make that a multiplication. So we're going to bring those exponents out in front. This is going to become 3x times the natural log of 4, and this is going to become x minus 1 times the natural log of 6. So the natural log of 4 and the natural log of 6, these are constants. There's no variable involved here. So these are things that you could just look up on your calculator. Okay. So I'm going to divide both sides by the natural log of 4. And I get 3x equals x minus 1 times the natural log of 6 divided by the natural log of 4. Now this guy right here, natural log of 6 over natural log of 4, I'm going to find that on my calculator, and that's going to make this 3x equals 1.8 times x minus 1. Now all I have to do here is distribute. So I get 3x equals 1.8x minus 1.8, and if I solve this for x, which is my last step, is just to calculate everything out and simplify, I get x equals negative 0.759. Okay. So this is one method. Now notice there's no natural logs, there's no e's. It's just a simple problem where I'm solving for a variable in the spot of the exponent, but I can use a natural log as part of how I would solve it, or how I would pull the variables out of the exponential spot. All right, let's look at our other method, our second method, and that's using ELBA. Okay. So the first thing we want to do is we want to rewrite this expression using ELBA. So when you use ELBA, you have two bases, and in this problem we have two bases. So you basically just have to choose which one you want to be the base. Okay. So for my base, I'm going to choose 6. Okay, this is going to be my base, and this is going to be my exponent, and then everything over here, this whole entire expression, this is going to be my answer. So I'm going to do exponent equals log base answer. Okay. So now I have this written using ELBA. Now I need to use the same property of logs I used last time, and that's namely anytime you have an answer that's raised to an exponent, like for instance I have this 4 to the 3x, I get to bring the exponent out in front. So I'm going to bring that 3x out in front. So that's x minus 1 equals 3x times log base 6 of 4. Now log base 6 of 4 I can find really easily by using my calculator. I can turn this into the natural log of 4 over the natural log of 6, right, using my change of base formula. Okay, so I use my change of base formula to convert this expression into this expression so that I can find it on my calculator. So now I have x minus 1 equals 3x times the natural log of 4 over the natural log of 6. And then when I multiply this out, I get 2.7x equals negative 1.8, right? And then this becomes x equals negative 0.759. And this is the exact same answer we got using our other method. So as you can see, there's really no difference. You can use either one, okay? So you can take the natural log of both sides, or you can use ELBA to rewrite it. You're still just going to go through the problem and set it up and solve, okay? Okay, so pause the video, take a moment to solve the problems on the back side of this worksheet, so that's problems 8 through 15, and then check in with each other, and then check the answers. So go ahead and pause the video now, and then just resume as soon as you're finished. Okay, homework tonight is on page 735, numbers 1 through 3, 9 through 17, and then on the next page, problems number 58 and 60. And I also want you to complete the laws of logs worksheet that you were working on at the beginning of the class, and I would like you to finish problems 10 through 28 evens. And I will see you guys on Tuesday.